Everyone to this lectures. Today we'll discuss the optical absorptions and band gap in the solid materials. I am Dr. Mananjan Ojha, Assistant Professor, Department of Basic Science Chemistry, SR University. So we'll discuss here the optical absorptions, the process. So what happen is that when a materials it absorbs a incident electromagnetic radiations, means one light it is absorbing, then how the internal process of electronic transition takes place inside the compound, that we are going to discuss here. So there are different kind of a light sources there. So based on the wavelength, there will be a visible light or ultraviolet light or infrared light. Depends on different kind of a wavelength. For example, visible is 450 or 372 750 nanometer, or IR infrared is the higher wavelength, and ultraviolet is the lower wavelength of the visible light. Now these light, when you are interacting with the materials or solid materials then what kind of electronic transitions is taking place in that molecules, which provides the informations about the molecules, and after knowing that one we can understand what is the applications of these molecules. So we'll discuss here what types of the interaction is taking places and what are the conditions for that one. So now let's say when energy one in a light is interacting, that is new, it is written here, it is interacting with the molecules, then some electronic transitions will happen in the molecule. That electronic transitions will happen from the ground state to excited state. When this happens, when electron is moving from ground state to excited state, we call this absorptions. In opposite way, when that electrons in the excited states now coming to the ground state, then this emit the energy, that light or radiation, that we call the emissions process. Right. So what is the condition that it will absorb the light, and which the exactly which electronic state or where which state it can reach, that we'll discuss in this chapters. Before that one, we'll understand first that from where the electron will transitions will takes place, and then where the electron will go. So for that one, we'll need to know that understand that electronic band structure in the solid. So there are the two type of the term we'll understand here: valence band and the conduction band. So in valence band is that in molecule where the all electrons is available there. So all electrons in one place, one band it is there. At in absolute zero, all the electrons it is occupying in this state. So that band we call is this is valence band. Now what conduction band is the one band which is higher than the valence band. Energy is much more higher than the valence band. We call it conduction band, where there is no electron. So valence band is full of electron, or conduction band is there is no electron, and valence band is lower in energy, conduction band is the higher in energy. Now there another term we call is the band gap. Let's say this is our valence band and this is our conduction band, then the energy difference between two we call is the band gap. So this band gap is energy differences between two band, that is called valence band and conduction band. Now for different materials, this energy gap difference or band gap differences, or that band gap for different materials has different. For example, for metal, if you see this valence band and the conduction band, they merge together or they mix together. So there is no particular any gap. It looks like continuous. So this portion is they are merging together. So there is no gap in the metal. So electronic transitions for the valence band to conduction band is very easy because there is no energy gap. Now, for semiconductor materials, if you see this energy gap between the valence band and the conduction band, there is a little energy gap. So means we need some amount of energy where the electrons residing in the valence band, so it can go to the conduction band. So electronic transitions happen by interactions of the light, incoming light or photons with the electrons in the valence band, and this energy should be sufficient that it will match with this gap between valence band and the conduction band. For semiconductor, this gap is very less, and for insulator this gap is very large. So now this energy difference between the valence band and the conduction band is very much large, so that's why we need very higher energy to excite an electron from the valence band to excited state. Otherwise, if this excitation is normally is not takes place for the insulator compounds, right? Now, this just we discussed based on that this energy gap differences. If it is there is no gap, that is conductors. It is generally observed in the metals. If small energy gap is there, we call the semiconductor. If this energy gap is very large, then we call it the insulator. So if we comparatively draw the valence band and conduction band, so this is there is conduction band and valence band. For this one is the metal, that is semiconductor, and this is insulator. So this is the energy gap for insulator, this is the semiconductor, and this is there is no gap, this is called the conductor. So in conductor, any kind of energy with small energy can apply here, so then electron can transfer from here to here. But for semiconductor, you need sufficient amount of energy that is also less, that is close to 0.123 electron volt in this region. Means in a compound, if the energy gap is 0.123 electron volt, then we consider that compound is the semiconductor. And if it is more than 3 electron volt, we call it the insulator. Compound is insulator. Now what happens is that when some light or incident light or photon is coming, there is a with energy h nu. Now if let's say this is your conduction band, this is valence band, and this is conduction band. Now electron is here, it should go from here to here in the valence band to conduction band. Now that I am providing here the photon or light here h nu. Now this energy gap is now let's say 0.5 electron volt. Now what is the photon I am providing? This energy of the photon, this photon energy must be greater than or equals to 0.5 electron volt, then only these transitions will happen. If it is less, then transitions cannot happen. So minimum criteria is that it should be equal to the energy gap, or minimum energy it can take, that is the energy difference between valence band and conduction band, or higher than that energy gap. So when we are providing the energy from outside through a light interaction, that should be equal to this gap, energy gap, or more than that energy gap, then only the electronic transitions can take place. Now here we'll discuss that two type of the energy transitions can happen, and so there is two type of the energy gap, the band gap, that is called direct band gap, indirect band gap. If you see here, this is called the momentum. This k value is represented as momentum. So this is axis is momentum axis. Now this is our valence band, and this is our maximum point, and this is conduction band, this is the minimum point. So when there is no change of k is same, and that interaction is taking place or transition is taking place from without changing the k, directly the interaction is taking place from valence band to conduction band. This process we call the direct band gap. So here what is happening, transition is taking place from the maximum point of valence band to minimum of the conduction band where K value does not change. So no change of K value. No K value change. So no K value change means there is no change in momentum. So when there is no change of momentum, the maximum point electrons from the maximum point of the valence band to the minimum point of the conduction is transition takes place, that we call direct band gap. Now opposite way, if the transition is taking places where K value is not constant or it is changing, so then we call it indirect band gap. Now let's say this is the maximum point of the valence band and this is the minimum point of the conduction band. Now if this transition is taking places here, now this here K value is 0, let's say, but here is K value is different. So as K value is different or momentum is different, then this process is called indirect band gap. So for changing this K value, this momentum is changing. For that one, some kind of a lattice vibration should occur. Otherwise, these transitions cannot take place. So means there should be a simultaneous involvement of the photon with and also phonon, that is called lattice vibrations. When these things has happened, then only the indirect band gap transitions may happen. So direct band gap transitions happened with galliums, and this is an example of direct band gap compound happened with this gallium arsenide or indium phosphide, whereas the indirect band gap happened for the silicon or germanium, for those compounds. So now here if you see that how the transition is taking places, that let's say this light we are providing from the outside, and these steps is our electronic states, ground state, this is excited state. Above one the excited state and below the ground state. And then every in this electronic state there is small state, this is called is vibrational state. Here also in excited state, in this small state is there, you call it the in excited state, in electronic state there is also vibrational state. Now when photon is interacted in the ground state with electron, then if electron will move to the excited state, then hole will be created, that is called hole. Means electron is shifted from, this is negative, shifted to the ground state to the excited state. When it is went, then here will create in the ground state one hole is there. Otherwise what happen, that if this energy will absorb in the ground state, and then it is not changing the electronic state, in the same electronic state, but vibrational state is changing, means from lower vibrational state to higher vibrational state it can move, right? When it is moving in the same energy level, same vibration, here in case electronic state is same, but vibration different vibrational level it is moving, so same band energy it is moving, we call this the intra band absorptions. But when with different electronic state this electron is moving, then we call is the interband absorptions. Here this is our the valence band and this is our conduction band. So from valence band to conduction band electronic state electronic transitions happening. So this is called interband absorptions. But here this light is coming interacting with the materials, and inside the material, that with this conduction valence band only transition is taking places. So there is not means small electron is not going to the conduction band. So this process is called intra band absorptions. And this one we have discussed, this is called exciton formations or excitonic absorptions, where one after interactions with the light, then one hole, one electron is creating, and it's a pair form, it's forming a pair. So this electron hole pair when it is creating, then we call it is a excitonic absorptions. This is called excitonic absorptions. Now, this what we called is the how to calculate the absorption coefficient and this optical spectra. I will calculate from here that we'll use, it's called Lambert-Beard law, that is I equals to I0 e to the power minus alpha x. So means, let's say this is our sample, then we are passing one light, that is intensity of I, and then after the passing the material, the intensity is decreases, that is called, this is called passing with the I0, and after passing this is I. So when I'm using one light source, before passing the interaction, passing the materials, that intensity is I naught or I0, that is higher intensity. After passing the material, the transmitted light intensity is I, that is lower. Then from using these equations, we are going to calculate the absorption coefficients of the material. So in practically also we can done by using what called alpha is nu to the power n and with the base of the lambda values. That plots is called Taku plot. So we'll get some kind of a constant value, and from there slope where it is interacting or touching in the x-axis, from there we can calculate. So that's how we can calculate the value of the band gap. The importance and the applications. So here this compound is this, what we need to know, that interactions of the materials with the light, because we can use in a different purposes. For example, a solar cell. One solar cell, what happens is that, so the materials first absorb the light, right? Then let's say this is a one materials. So when put in the sunlight, so it will absorb the lights. Then what it will do, it eject the electrons from the that state, then creating a hole here. Now hole means positive in sign or nature. So now this positive type is coming in this side, then electron is moving in this directions. Then in the solar cell, other counter it is coming this electron. Now this side is plus and this side is minus. Then we are getting the electricity. So this kind of happened in the solar cell. For this electronic transitions should happen, we need to know the band gap of the materials, and then we can provide that, so we can calculate or can understand that solar light, that light we are going to this natural light or solar light we are using, that is sufficient for that electronic transitions or not. If it is sufficient, then only it takes place in the solar cell, otherwise we can't use that material for the solar cell. So that's why one important that we need to know that which means what compound can be used for which purpose, like for photo detector as well, for the LED and laser as well, and optical coating also we can use by understanding that how the inside or in molecular level, how the electronic transitions or can takes place inside the molecule, or how it interact with the light. So that is very important to know the applications of the materials. Now, how to calculate of these materials? So, can energy gap or for different materials? By here is some examples we can discuss here, that we are practically wants to know to calculate the difference energy gap or light, minimum light can be used for our electronic transitions. Let's say we have a semiconductor which it can absorb at 620 nanometer, means we know the materials, and that can absorb 620 nanometer the light. Then I want to calculate the what is the band gap, right? So how can we calculate it? So what we can do is that, so band gap we are calculating here is from this light at 620 nanometer, we are going to calculate that what is the band gap for this materials, band gap energy. So I will do that. So band gap of the energy or energy of the materials will calculate by using, that is called E equals to h nu, and nu equals to this, nu equals to c by lambda. So now this equation is h into c by lambda. So this is the Planck constant and c is the velocity of the light. When we'll multiply this one, then we can get, and that which light we are using for the wavelength, from this one we can get the band gap energy. Now for this is the energy, this is called h nu is energy. Now what we need to convert it, this energy, into, we as we are measuring here electron volt, then this energy from joule to, we need to convert it. So then if we convert this one, then the value will get, that is called 1239.8, sorry, 84 electron volt, then nanometer divided by lambda. So that's why directly this equation is used. In the approximate value here is taken 1240. So exact value may be 1239.84 electron volt and nanometer. So what we have done is that we have convert this one to a joule to electron volt. How we converted it? That 1 electron volt equals to 1.602 into 10 to the power minus 19 joule. So from joule we are converting to the electron volt. So if simplest way, that if we will divide 1240 divided by wavelength, that is in nanometer scale or nanometer unit, then directly we will get for electron volt. So here is equals to, so 1240 divided by 650. So I am using the wavelength of the 620 nanometer. So then we got the 2.0 electron volt. Now previously we have observed also that for semiconductor, that wavelength, this energy gap is 0.1 to 3.0 electron volt. So now it is 2.0 volt, means this materials actually a semiconductor materials, right? So and it is used for the LED and solar cell as well. Now here, what does, what is the energy gap? You know that band gap, that from conduction band. So for example, this is your valence band and this is your conduction band. Now this band gap is 1.8 electron volt, right? Now let's say I want to excite this electron from here to here, then I need some light from outside to excite the electron from valence band to the conduction band. Then for light, what the wavelength of the that light should be, incident light should I need to take, that which will be sufficient for this electronic transitions from the valence band to conduction band. This energy gap is 1.8 electron volt. So here is 1.8 electron volt we are talking. The difference means again it is giving the information this is a semiconductor. Now we can use the same equation here. So previously as we used, that is energy gap Eg equals to 1240 by lambda. Now we have just extension lambda, we are taking this side and Eg is coming this side. So this is 1.1240 in approximation divided by 1.8, so equals to 688.9 nanometer. So means for this electronic transition, that the materials having the valence band and conduction band difference is 1.8 electron volt, that is close to, let's say this is 690. So 690 nanometer wavelength of light is sufficient for this electronic transitions. So for electronic transitions, now this we can use close to 688 or 688 nanometer of the light, or lower nanometer of the light will be okay for this electronic transitions. Minimum we need that 688 nanometer for this wavelength of light for these excitations. Alright, now we are going to calculate that band gap from the Taku plots. So in Taku plots means this is called Taku plots means what we are doing, we are plotting that alpha age nu in n by this in y-axis and axis is age nu from this plot. So this is our y-axis and axis is age now. Here n value is depends on the materials. So means there is for different transitions n value will be different. For let's say this is for direct transitions. So means we discuss the direct transitions of the electrons, right? So there is k value is 0. So for in that case n value will be different. That is called n value will be different, and for the indirect transitions, so n value will be different. So maybe it will be half or two. For let's say independent, so indirect electronic transitions, for that n value equals to 2, or for direct transitions n value equals to half. So that's why it will also, these are allowed transitions. If not allowed transition, non-allowed transitions will happen, or forbidden transitions will happen, then n value also will change from 3 or something like that. So let's say we are using this as a n value. We do not know which materials we are calculating, so we are writing as a n. Now we are plotting that alpha age nu to the power n versus age nu. Now what then we'll get the plot. In this plot, then we'll get a constant here from this one, then we'll get a slope, which one this x-axis is crossing by this slope. That point will tell this is a band gap of the materials. If it is touching that point is 3.2 electron volt, then we can say for that material it is the band gap is 3.2 electron volt. Like this we can calculate for the electronic band gap of the different materials from the tuck plot. So means in this plot what we are doing, we are plotting a graph alpha age nu to the power n based on the materials. If it is n indirect then 2, then if it is direct half, or for forbidden then it is 3, something like that, versus age nu. Then in this plot we are making one slope which is touching to the x-axis, that where it is touching the x-axis, and that point is the band gap for the materials. So now you want to classify the materials from the experimental results. Let's say you know that band gap is 0.7 electron volt. Then it is questions asking that what is the material for this one, what is the material type, means it's a conductor or semiconductor or insulator. Now remember, this way for metal there was no energy gap between the semiconductor valence bond and conduction band, whereas for the semiconductor that this gap between the valence band and the conduction band was 0.123 electron volt. So it is in between this range. So that's why this compound is known as the semiconductor in nature, right? So from this value we can classify it, that which materials is which category, right? And you can use for your applications purpose by knowing the energy gap differences. Now electron volt you know, and previously what we have done is that we converted joule energy to joule, that is energy unit, to electron volt. Both are in energy unit but in different unit it is. One is electron volt and another is joule. So now if joule you know, so 1 electron volt equals to 1.602 into 10 power minus 19 joule. So it is 2.5 electron volt. Now it is converted to joule, then how much it will be? So we will simply multiply with 2.5. So it will be 4.005 into 10 to the power minus 19 joule. So this process is only about that how the energy unit conversion can be done. Now, for example, here two compounds is given to you. Then you tested these two compound. So you studied these two compound A and compound B. Then you calculated the energy gap. between band gap for these materials. Then from the study, what you got that for material A, this energy gap from the valence band to conduction band is 1.1 electron volt. Whereas for materials B, you got that energy gap or band gap from the from between the valence band and conduction band is 3.4 electron volt. Now, from this result, what conclusion you are getting? So, for materials A, this energy at the band gap difference is 1.1 electron volt, which is in the range of 0.1 to 3 electron volt. This is for semiconductor. So means these materials can be used for the solar cell because it's a nature in semiconductor, and also it absorbs the infrared radiations. Means you can change or the wavelength of the light from the electron volt to wavelength lambda values, then you can see that it is in the infrared radiations of the light. So electron volt we can make it in joule, that is h nu, and from this one lambda we can calculate lim equal to c by lambda. So we'll convert to the joule, then from that one we can calculate the lambda value as well for understanding the what is the region for the materials, means radiations. Now another material that is 3.4 electron volt, which is outside of the conduction band. So it is going to insulator. If it is insulator, it is going to, so energy gap is very high. So energy gap is very high means this is going to the ultraviolet radiations and suitable for UV photoelectric or transparent devices. It cannot be used in the solar cell because it is in insulator in range. Now that's where I am talking the UV or infrared, that we are talking about the different kind of wavelength. The wavelength of the UV is much more shorter or smaller, which is high energy, and higher is the small, higher in wavelength, this less energy. So we can convert this electron volt to joule energy, and then from there we can convert it to lambda values. How will convert? Let's say this energy will convert H nu, this is equals to energy. This energy equals to, let's say, 1.1 electron volt. So we'll multiply 1.1 into 1.609 into 10 to the minus 19 joule. That is the energy value. Then what we'll do? We'll H nu, H into nu equal to C by lambda. Now we'll divide this one with C and A, then we'll opposite, make it opposite, then we can get the lambda value, then we will come to know that which radiations it is matching, whether infrared or ultraviolet, right? So this we have discussed that what the transitions of the electronic transitions takes place in the materials, and how to calculate the band gap or radiations of the light, wavelength of the radiations of the light, and what is the properties of the materials can be used for which applications. Thank you.